Thanks for attending this training on MEMS microphones. The MEMS microphone market can be divided into three major segments: notebook and netbook computers, smartphones and tablets, and accessories. Each market segment has its own unique set of requirements. Most notebook computers use digital MEMS microphones for noise immunity and for performance matching in a relatively large top port package with a standard footprint. Mobile applications such as tablets and smartphones are most concerned about performance and size, and use both analog and digital microphones with both top and bottom ports. Finally, accessories such as corded mic headsets primarily use analog microphones for compatibility with analog mic inputs and for low latency in applications such as noise-canceling headphones. ST makes three digital MEMS microphones. The MP45DT02 is designed with the notebook computer market in mind. It is a top port microphone in a 3.76 by 4.72 millimeter footprint, a digital PDM output, and has 61 dB SNR. The MP34DB01 is a bottom port microphone in a 3 by 4 by 1 millimeter package with a digital PDM output and 62.6 dB SNR. Finally, the MP34DT01 is a top port microphone in a 3 by 4 by 1 millimeter package with a PDM digital output and 63 dB SNR. What sets ST's microphones apart from our competitors? Performance. ST's high-performance sensors and proprietary packaging technology allow us to produce microphones with a very high signal-to-noise ratio, the primary measure of microphone performance, and very wide frequency response. ST's 3 by 4 by 1 millimeter digital microphones have a very flat frequency response over the full audio band from 20 Hz to 20 kHz. The frequency response of our competitor's microphone is not as good, as you can see in this graph, and the same is true for their SNR. The other advantage that ST has is our MEMS manufacturing capacity and expertise. ST's manufacturing capability allows us to respond very quickly to changes in volume, and our economies of scale allow us to offer very competitive pricing. The heart of the MEMS microphone is the acoustic sensor. The acoustic sensor uses a fixed plate and a movable membrane to detect sound waves. Sound waves cause a change in pressure, which causes the membrane to move, which in turn causes the capacitance between the membrane and the fixed plate to change. This change in capacitance is then measured and converted into an electrical signal by a CMOS interface IC. MEMS is short for Microelectrical Mechanical Systems. MEMS devices are constructed using silicon wafers with processes similar to what are used for fabricating ICs. What sets MEMS apart from traditional ICs is the ability to create physical structures with moving parts in the MEMS devices. MEMS acoustic sensors have three main parts. The base of the acoustic sensor is the silicon die that the microphone is built on. A flexible membrane and a fixed plate are built on top of the silicon base using chemical deposition and selective etching processes. This is an exploded view of the MEMS sensor inside ST's microphones. The MEMS sensor has a silicon base, a layer that provides electrical isolation for the membrane and the backplate, a flexible membrane that forms on one side of the capacitor, and a fixed plate that forms the other side of the capacitor. A hollow cavity is also etched in the silicon base beneath the membrane. On top of all this are pads that allow us to make electrical contact to both the fixed plate and to the membrane. The fixed backplate and movable membrane convert sound waves into an electrical signal. Differences in pressure on opposite sides of the membrane cause it to move, which in turn creates a change in capacitance between the membrane and the backplate. ST's MEMS microphones are multi-die devices that are made using a MEMS acoustic sensor, an IC that converts the change in capacitance in the sensor into an analog or digital output, and a hollow package with a sound port to let sound in. The design and manufacturing expertise that ST has developed for other MEMS products, such as accelerometers and gyroscopes, Our large investments in MEMS manufacturing capability and our control over our full supply chain gives ST a clear advantage over our competitors. This is a block diagram of the IC that's used in ST's MEMS microphones. The portion inside the green box represents the sensor with its variable capacitance. The IC circuitry is shown inside the yellow box. The IC places a charge across the sensor capacitance, measures the change in voltage across the capacitor as the capacitance changes, and then amplifies the signal. In this case, because it is a digital microphone, the IC then uses a delta sigma modulator to convert the analog signal into a pulse density modulated output. There are 3 signals on the digital MEMS microphone: a clock input, a left-right channel select input, which allows you to connect more than one microphone to a single data line, and an output. ST's digital microphones use pulse density modulation to encode the audio signal. Pulse density modulation is similar to the pulse width modulation that is used in Class D amplifiers. Pulse width modulation uses a fixed frequency and a variable pulse width, while pulse density modulation uses a fixed pulse width and a variable frequency. The audio signal can be recovered from the microphone's PDM output by measuring the ones density in the PDM data stream and filtering the results. There are 3 key microphone performance parameters. The sensitivity of a microphone is its response of the microphone to a particular sound level. Sensitivity is normally measured in decibels relative to full-scale output, or dBFS, for digital mics, or decibels relative to 1 volt, or dBV, for analog mics. The sensitivity of the microphone can be adjusted by increasing or decreasing the gain of the internal amplifier. Changing the gain of the internal amplifier does not affect the signal-to-noise ratio because both the signal and the noise are amplified equally. However, the sensitivity of the MEMS sensor is an important factor in determining the signal and noise ratio of the microphone. A stronger output from the sensor requires less amplification to achieve the desired sensitivity, so the noise is not amplified as much. The noise floor is the output of the microphone when there's no sound present. Like sensitivity, the noise floor is specified in dBFS for digital mics or dBV for analog mics. Normally, the result of the noise floor measurement is filtered using an A-weighting scale so that the measurements more closely reflect what humans hear. The signal-to-noise ratio is the difference between a microphone's sensitivity and its noise floor. The SNR is measured in dB, and it is the most important single measure of microphone performance in most applications. 2 other important microphone performance parameters are the acoustic overload point and the dynamic range. The acoustic overload point is the maximum sound level that a microphone can capture faithfully. The acoustic overload point normally is specified as the sound pressure level where the total harmonic distortion exceeds 10% and is specified in dB/SPL. Finally, the dynamic range of a microphone is the difference between the acoustic overload point and the noise floor, which are the maximum and minimum sound levels that it can capture. Dynamic range is specified in dB. The ability of the MEMS sensor's membrane to flex in response to sound waves determines the sensitivity of the MEMS sensor, which in turn has a large impact on the signal-to-noise ratio. ST uses a unique 4-point anchoring system that gives our membrane additional flexibility and provides a greater response to a given sound pressure level. Our competitors anchor the membrane all the way around the perimeter, which limits its sensitivity and results in a lower SNR. Microphone packages are also a critical factor in determining their performance. MEMS microphone packages are hollow and have a sound inlet to allow sound to reach the MEMS sensor. The front chamber of a microphone is the area between the sound inlet and the sensor membrane. Small front chambers provide better performance, particularly at higher frequencies. The back chamber is the area inside the microphone on the opposite side of the membrane. A large back chamber will improve the sensitivity of the MEMS sensor, which will in turn lead to an improvement in the signal-to-noise ratio. A large back chamber will also improve the low-frequency response. In order to achieve the best performance, microphones should have a small front chamber and a large back chamber. Most bottom port microphones have similar designs. The sound inlet is on the bottom of the package, and the MEMS sensor is placed directly over the sound inlet. This creates a small front chamber, which provides good high-frequency response, and a large back chamber, which provides high SNR and good low-frequency response. Top port microphones are a different story. Top port microphones have a sound inlet in the top of the package instead of the bottom. However, in our competitors' microphones, the sensor remains on the bottom of the package. This creates a large front chamber and a small back chamber, which hurts the signal-to-noise ratio and the frequency response at both the low and high ends of the audio spectrum. These differences explain why bottom port microphones have traditionally had better performance than top port microphones. The difference in performance between top port and bottom port microphones creates a dilemma for customers that prefer top port microphones. Customers frequently would prefer a top port microphone because it's easier to protect top port microphones from contamination during manufacturing. There are also many applications where a top port microphone makes more sense than a bottom port microphone. However, choosing a top port microphone has traditionally meant sacrificing performance, so customers have been forced to choose between performance or manufacturability. ST took a completely different approach to top port microphones. The sound inlet is on the top of the package, but ST's packaging technology allows us to mount the sensor to the bottom side of the lid, instead of having to place it on the bottom of the microphone as our competitors do. As a result, the geometry inside ST's top port microphones is basically the same as our bottom port microphones. A small front chamber provides good high-frequency response, and a large back chamber gives us good SNR and good low-frequency response. In addition to providing a top port microphone with better performance than what has previously been available, this also greatly benefits applications that use both top port and bottom port microphones for applications such as noise cancellation applications and beam forming. Close performance matching between microphones is necessary to achieve the best results in these types of applications. This X-ray photograph of ST's MP34DT01 top port digital MEMS microphone shows the MEMS sensor and the CMOS interface IC attached to the bottom side of the package lid. The sound inlet, the hole that allows the sound waves to reach the sensor, is directly above the MEMS sensor. Wire bonds connect the interface IC to the sensor and to bond pads on the package. The substrate is soldered to the lid and sealed, creating the back chamber. This is the frequency response of one of our competitors' bottom port digital MEMS microphones. You can see that in this case, the low frequency -3 dB point is at about 75 Hz, and there is a resonant peak of about +8 dB in the response, somewhere around 12 kHz. This manufacturer claims to have a bandwidth of from 75 Hz to 20 kHz in their specifications table, but if you look further back in their data sheet, you can find this plot in the typical performance section. This is a plot of the frequency response of another competitor's top port MEMS mics. Like the plot on the previous page, this graph was taken from the data sheet. In this case, you can see that the low frequency response is down about 1.5 dB at 100 Hz, but at 10 kHz, it's up by 5 dB. This is because of what we were talking about earlier in terms of the large front chamber causing poor high-frequency response. Microphone data sheets often only show the frequency response between 100 Hz and 10 kHz in order to make the response look as flat as possible. This is the frequency response curve for ST's MP34DT01 top port digital MEMS microphone. You can see that the response of the MP34DT01 is flat to within about 1.5 dB from 100 Hz to 10 kHz, and remains fairly flat from 20 Hz to 20 kHz, with no resonances within the audio band. Before MEMS microphones were available, most consumer products that needed a microphone used electric condenser microphones, or ECMs, and some consumer products still use them. However, most customers are switching from ECM microphones to MEMS microphones. This next section will show why. ECM microphones are relatively inexpensive, and they have pretty good SNR. However, ECM microphones have several disadvantages compared to MEMS mics. They have relatively poor sensitivity matching from unit to unit. This isn't too important when you're only using a single microphone, but applications that use multiple microphones for things like noise cancellation or microphone arrays require good sensitivity matching to get the best performance. The sensitivity of ECM microphones also shifts during SMT soldering processes, and they have a high temperature coefficient. They're also not as robust mechanically. On the other hand, MEMS microphones provide high performance in small packages, consistent performance with excellent sensitivity matching from unit to unit, very little change in sensitivity with temperature, SMT compatibility, and mechanical robustness. The other advantage that MEMS mics have over ECM microphones is the availability of microphones with digital outputs. The digital outputs on our MEMS mics don't require any analog signal conditioning or an external ADC. Digital mics also have inherent EMI immunity, which makes them ideal for use in high-noise environments like notebook computers. This is one of the main reasons that notebook computers switch to digital MEMS microphones from ECM microphones. This shows the frequency response of some representative ECM microphones and ST's MP34DT01 digital MEMS mic. There are two things to note with respect to the ECM microphones. Their response is not flat, and their response is not the same from unit to unit. In comparison, the MP34DT01 response is very flat and very repeatable. This slide shows the temperature sensitivity of some representative ECM microphones and ST's MP34DT01 digital MEMS mic. As you can see, ECM microphones are very sensitive to temperature, and their sensitivity can go up or down. This is a real problem in applications using more than one microphone, because noise cancellation and beamforming algorithms rely on sensitivity matching between microphones for good performance. On the other hand, the sensitivity of ST's MP34DT01 does not change very much with temperature and is very repeatable from unit to unit. ST has two digital MEMS microphones in a 3x4x1 mm package, one with a top port and one with a bottom port. Both of these microphones have outstanding SNR and frequency response. Both mics also have very low distortion and excellent power supply rejection. They both have an acoustic overload point of 120 dB SPL, and their sensitivity is -26 dB FS. The third microphone that ST makes is the MP45DT02. This microphone is in a 3.76 by 4.72 by 1.25 mm top port package and has a digital PDM output. It has a 61 dB SNR and a 120 dB SPL acoustic overload point and excellent distortion and PSRR. The sensitivity is the same at -26 dB FS. ST has evaluation boards for all the MP34DT01, the MP34DB01, and the MP45DT02. All of the boards have both USB and I2S audio outputs. The USB output allows you to connect the evaluation board directly to a PC. The evaluation board looks like a USB microphone to the PC. This allows you to use it with any PC applications that use a microphone, in exactly the same way you would use any USB microphone. The boards also have I2S outputs for use with audio analyzers, such as Audio Precision. This is a block diagram of the microphone evaluation boards. This shows how easy it is to interface a digital microphone to a microcontroller. The boards use an STM32 microcontroller to capture the outputs of two microphones, convert the data from PDM to PCM format, and output the results on USB and I2S. The clock inputs of the microphones are driven by timers in the STM32, and the microphone outputs are captured by two SPI ports. The conversion from serial PDM audio data to PCM format is performed in software. STMicroelectronics is the undisputed leader in consumer and mobile MEMS. That's a quote from one of iSupply's consumer mobile MEMS market tracker reports. You can see from the data how ST dominates the consumer MEMS market. In 2009, we were just slightly higher than our nearest competitor, which at that time was Avago. But our tremendous growth over the last 2 years has launched ST to the top of the market. In 2011, the overall market for consumer MEMS devices rose by $420 million. ST captured almost 3/4 of that growth, $300 million. Here are a couple more quotes from the same iSupply report. In addition, ST has been a leader in audio semiconductors for more than 40 years, since creating the world's first power IC in 1969. In 1994, ST developed the world's first Class D audio amplifier IC with an output power capability of up to 10 watts. In 2006, ST developed the world's first single-chip digital Class D amplifier with I2S digital audio inputs, integrated digital audio processor, and 2x20-watt output power capability. Since 1969, ST and its parent companies have developed more than 100 different audio power amplifier ICs, ranging in output power from 40 milliwatts to 400 watts. For more information, please visit www.st.com/MEMS.